So let's make this a little more quantitative. So let's think a little bit about the rates of these reactions. So if a reaction's rate is determined by a single barrier crossing, then the rate constant will be proportional to, and you can show this with various, collision theories, P times Z times e to the minus activation energy over RT. Now, what are these? Well, P is the fraction of collisions with the right orientation. Z is the frequency of collisions, which if you have bigger molecules, you'll get more collisions. But, the book talks a little bit about these, but it's really hard to actually get these right. P and Z can't really be measured directly, so we use, instead of this equation, we just say it's some constant A. Where does A come from? I don't know. It's some prefactor. We don't really worry too much about it. We can solve for it if we have enough data, but we don't try to inspect the innards too much. Times, and this is the part that we can do a lot more with, exponential minus activation energy over RT. And so therefore, if the temperature goes up, then the rate goes up in a very well specified way. P and Z don't really depend on temperature, or a very, very weak dependence on temperature. If the temperature goes down, then the rate goes down. And this is the factor that we see in every day. If you want to have a reaction occur, you turn up the heat, so it's more likely to occur. If you want to stop reactions for occurring, you put something in the refrigerator, and all the kinetics slow down quite a lot. And they slow down, the speed changes quite significantly with small changes in temperature. So we've got this reaction. Well, let's look for a more useful form. Like, a problem with that, if we're just calculating the rate straight out, is that we need to know this prefactor, and which, it's a number that you need to carry out a lot of experiments to get. So instead, if we know the rate at 2 values of T, then we can eliminate that unknown and solve directly for the activation energy. So for example, let's take a look at this equation. Let's take the logarithm. There's an exponential in there. Maybe we can get rid of the exponential. Then we get the logarithm of the rate is equal to minus activation energy over R. And now I'm splitting up this part a little bit. Activation energy, times 1 over T plus log A. So this is nice and linear, right? Already we see that it's nice. And then we do the same thing at a second temperature. So it's going to have a different rate, but the prefactor will be the same. This should look very similar to something you've seen before, like boiling point elevation with temperature. It's the exact same initial equation, the same exponential relationship between, in one case a rate and another case a vapor pressure, and some energy. So if we subtract these two, then what we get, we can rearrange to get the logarithm of the ratio of the rates is equal to activation energy divided by R times 1 over T2 minus 1 over T1. Again, this looks very much like the vapor pressure equation, right? The same pattern of before. Now we had the log of two things. Here we've got the log of two things. We have R over some energy, and we've got this 1 over T2 minus 1 over T1 factor. So it's the exact same math as you've seen before, because you have this relationship that keeps coming up, something being proportional to the exponential of an energy. Yep, and that's because, that's the vapor pressure is equal to an exponential times an exponential of the vapor pressure, the heat of vaporization. Okay, so the first order isomerization reaction of cyclopropane to propene. So these molecules have the same molecular formula, but different bonding. So it's called an isomerization. Is a rate constant of 1.10 times 10 to the minus 4th inverse seconds. It's a first order rate constant, right? So it should be in the form of microseconds. And clearly, it's this just depends on the concentration, right? There's nothing else around, so it's just the concentration of the reactant. And then a rate constant of 5.70 times 10 to the minus 4th at 500 C. What's the activation energy for this reaction? Okay, so let's see if we can figure that out. So we're going to be using the Arrhenius equation, and that is log of K1 over K2, the log of the rates, is equal to activation energy over R times 1 over T2 minus 1 over T1. And that is log of 1.1 times 10 to the minus 4 inverse seconds of 5.70 times 10 to the minus 4 inverse seconds. And the inverse seconds cancel, which is good whenever we're taking a log. We should have something with no units, equals log of 0.193 is equal to minus 1.645. Okay, so we have minus 1.645 is equal to activation energy over R. And remember, all of these formula use Kelvin temperature. So let's convert to Kelvin. This becomes 470 plus 273. That's 743. This is 500 plus 273. That's 773. So this is 1 over 773 minus 1 over 743. I'm going to rearrange this a little. I get that because we're solving for EA. So we get that EA equals minus 1.645 times 0.008314 kilojoules per mole Kelvin. We see that this ends up being minus 1 Kelvin over 5.22 times 10 to the minus 5th. Obviously, this is quite small. This is two large numbers that are close to each other subtracted, but note that, that this number is larger than this one, so the answer will be negative. And so we get 262 kilojoules per mole is the activation energy there. And so this is perfectly reasonable activation energy, somewhat high, right? Because it's about the size of a molecular reaction. They're always positive, so that's one thing you can check on this. If you don't get that it's positive, there's a problem. What you'd see is if it actually got slower at higher temperature, that would be indicative of a negative activation energy, but that doesn't make any sense. That's impossible. So that's one thing you should be looking out for. Okay, so that's how we use the Arrhenius equation to figure out activation energies. And we'll see some other applications in the next section as well. But that's you can as well, if you know the activation energy and know the rate and know the rate at one temperature, you can figure out how much it gets accelerated at another temperature. Though the most common situation is measuring the rates and from that figuring out what the activation energy had to be. All right, that's the end of this segment.